Good morning. So let's start this keynote session on Bioinspired Robotics. My name is Paolo Dario. I'm at the Scuola Superiore Sant'Anna in Pisa. And actually, I've been inspired by many sources to work on Bioinspired Robotics together with my colleagues. Maybe next slide. Take some time. Why? Because it has videos. And those videos are just a living representation of what bioinspiration is and why we are fascinated. Actually, there's a lot of hype today about artificial intelligence, but I must say that I'm more interested in understanding, for example, the graceful behavior, so the science and technology behind the graceful behavior of a cat. And if you look, actually, if you can make the video run, you will also be fascinated by the ability of animals, of course, also octopus, also plants. But there is another source of inspiration. Is the fact that Leonardo da Vinci, Leonardo da Vinci means Leonardo born in Vinci. And Vinci is a small town that is just 35 kilometers from our Biorobotics Institute. And Leonardo da Vinci is certainly a figure that is extremely inspiring till today. So for example, you see what he wrote about the human body as a wonderful machine. And obviously, he was interested, actually probably was one of the first in the world to combine arts with science. You see here how he observed, analyzed the behavior of many biological systems, so in zoology, in botany, and of course, in the human anatomy. It's fantastic. At the same time, he was a wonderful engineer. At the time, of course, he didn't have the energy source, he didn't have the materials, and what really made it possible to make the design. But he was really inspired by nature, and he combined the analysis of a systematic, scientific analysis of biological systems with engineering. So here I borrowed a scheme presented by Cecilia Laschi and Barbara Mazzolai, who are here, by the way, who published a paper. I also published something on science robotics, by the way, on this. That is Science for Robotics, Robotics for Science. But it's about the connection between biology and robotics. That is no longer just observing and trying more or less to imitate, but it's something much more insightful. And today, we are addressing this fascinating field with the help of four distinguished speakers who are really leaders in the field. So, Kyu-Jin Cho from Seoul National University in Korea, Dario Floriano from APFL in Switzerland, Talia Moore from the University of Michigan, and Yasemin Ozkan-Aydin from University of Notre Dame, also in the USA. So without further words, I'd like to give the floor to Kyu-Jin.
Okay, thank you very much, Paolo, for the introduction. I'll be talking about Bioinspired Robotics, which I've been working on for quite some time now. I would like to start the talk with rethinking about how do we build robots. Right? These days, we have so many humanoids that's coming out. We start with an engineering problem, you design the body, and you attach sensors, embedded systems, and these days, because of the machine learning, like VLAs, everything, we have like fascinating robots. And we do experiments, and most of the time, there's a lot of iterations in each step, and of course, there's some large iterations as well, but it's mostly like sequential approach. How about nature? Learning, there's 3 layers of learning in nature, right? If you think about it, the highest layer is evolution, which learns across generations. And structures and materials are optimized by selection. And you can think of it as that intelligence is stored in its form and function. And then there's development. It's learns through growth, right? Bodies adapt based on the use and the environment, and form adjusts to the function. And the third, the last layer, is the neural learning. It's a real-time behavioral adaptation, trial and error, memory and control, and feedback driven. So at this point, we have a lot of advancement in the neural learning part, so that's why we have so many nice working robots. But I'd like to think about what we can do with the evolution part. Right? There's a big difference between evolution, learning by the evolution, and the machine learning. Mostly intelligence is embedded in form and material, and machine learning intelligence is embedded in weights, models, and policies. So Bioinspired Robots, I think it's about tapping into evolution's design archive, right? We have so many natures like insects and animals, so we're trying to find smart solutions from nature to overcome unstructured extreme environment. And Bob Fu used to always say that you will fail miserably if you try to copy nature because nature is way too complex. So what we should do is we should try to extract key principles and use the best engineering solution and try to embed control to the body parts. So I had the pleasure of meeting Bob Fu about 2-3 years ago. So the process of Bioinspired robot design goes like this. You start with a problem, you observe some motions in nature, and you try to abstract principles and certain design criteria. And you try to find that mechanical intelligence for adaptive, robust, and simple control. And then based on that, you try the development, mechanism design, and fabrication based on the best engineering solution you have. And these days, we have like soft robotics, where we tap into like soft materials for design. So it's getting better and better. And then you verify, and you do experiments, and you have fun. And you iterate until you find the real good principle that you can use. And by doing so, we are basically going back and forth to nature and robotics, right? We are trying to find the principles in nature to design robots with principles. And hopefully, we'll find the real solution for those examples. So this was my first take on for Bioinspired Robot, which was jumping on water. And the observation that I had was about from the fleas. Flea had a special morphology called torque reversal by a trigger muscle, where the muscle, the extension muscle, is originally put at a place and you can pump in a lot of energy, and then a trigger muscle actually pulls the extensor muscle and then thereby releasing the energy. So what's happening here is at the flexion state, it's at a stable state, and you can pump in a lot of energy in the extension muscle, and then what happens is, with the trigger muscle, the flexion becomes unstable and the extension state becomes stable. So it's changing the stable position. It's almost like a bistable stability, but except it's a controlled bistability. So with this principle, you can actually store a lot of energy easily and then release them by pulling a slide muscle. So we named this principle torque reversal mechanism. So you can see this. Imagine that spring, the red spring is a muscle. You can store a lot of energy, and then you pull the trigger, and then boom, it can jump. So it's compared to the escape mechanism. We thought that it could actually distribute the force, which is really good for jumping on water. So we kept on developing the designs. So we started with actual flea-inspired robot, then simplified the robot, and we built the robotic water strider. And we were able to actually create a robot that actually jumped on water. So this experience, which was a very positive experience for us, actually gave us a lot of confidence on believing in design, evolution design. So mantis shrimp also has this kind of torque reversal mechanism. So we tried to create this kind of torque reversal mechanism based on elastomers. So what we did was we created an elastomer, and we didn't want to use extra trigger muscles, so we are using a single muscle that could actually trigger the torque reversal because of the hyperelasticity of the elastomer. Because of the hyperelasticity of the elastomer, you can see that even though you're just keep on pulling the tendon, actually it passes through the center of rotation, and boom, it can actually create this kind of impact force. So you can see this kind of snap-through occurring, and using that principle, you can create motions. You can create this kind of motions. You can create a finger. You can create fingers that could actually grasp really quickly at high-speed swing, and so on and so forth. Another example is a deployable gripper in nature. it's a chameleon's tongue, which is basically, it has a preloaded geometry which powers the extension. And the tongue tip actually adapts to the target shape via the tip geometry. So we were inspired to create this kind of gripper that could actually do something like this. It just shoots and grasps any kind of object. So what we designed is it's a soft deployment mechanism for suction cup. Basically, we have a cold spring, and we have an extra chamber that can hold a vacuum. So it's a spring-inserted gripper body, which can actually elongate, and with the vacuum, it can actually pull. So basically, this is geometrically driven. It's basically mechanical design. It's physics-based mechanical design. What's happening is we have a three-way valve which actually disconnects the spring-loaded chamber, so you can actually pull the deployable gripper, and then as soon as you open this three-way valve, what happens is you have a chamber now which actually is open to the atmospheric pressure, and now it deploys, and as soon as the suction cup is closed, now the vacuum can work again. So now it automatically pulls up. So it's very just simple mechanical design, but what it can do is it can do like dynamically grasp moving objects, and it's a robust to error or vision sensing because it doesn't really need any kind of vision sensing. It's all mechanical-based sensing. So you can even grasp that kind of tilted objects. So imagine if you want to pick up objects at a different height, you normally have to control the height of your arm and grasp something. You don't need to control the height of your arm. You just go to a certain height, and then you deploy your arm, and as soon as the suction cup is closed, it actually picks up the object, and you can go. So it's very highly adaptable. And also, since it's very highly adaptable, you just deploy your suction cup, and it can actually grasp this kind of balloon at a very high speed. Imagine you have this kind of transparent trace, which is not that easy for the vision to recognize at a tilted state. You don't need to actually recognize the exact position of all those objects. It's just you can actually shoot and deploy, and it will automatically pull up the objects, thereby which will make things easy to grasp. No need for computation, no need for sensing. It's all based on mechanical intelligence. So if you want to pick up like multiple objects, normally there's grippers that has multiple of these suction cups, but they're all at the same height. But if you do this kind of multi-array suction cup, you can pick up objects at different heights. So basically, we are trying to use this kind of gripper at unstructured environments. So you can even do this kind of a narrow gripping. Another example that I'm going to show you is assembly of 3D printed hand with bioinspired joint. So we got interested in creating a bioinspired hand. And if you look at the hand, we were actually quite overwhelmed by all the hand designs that were out there, prosthetic hands, DARPA hands, and so on. But what we didn't like was it has so many parts. It takes so long to assemble all these one by one. And if you look at how nature creates these articulated mechanisms, it doesn't assemble, it grows, right? It starts from, and it can grow. Imagine if it was a pin joint, which all the robots use right now, you cannot grow, right? But because they're rolling contact joints, you can grow it, which is very analogous to 3D printing. You print by growing, right? So we thought maybe we can use 3D printing to remove assembly. We all know that 3D printing allows you to build anything you want, but that thing is a structure. It's not a mechanism. As soon as something has to move, you have to assemble them by one. Of course, there is things like single-step printed this kind of joint that you can see in the exhibitions, but actually there's always this kind of a gap. And because of this gap, you can only use it as a demo, but not as a real thing. So what can you do? So what can you learn from the human metacarpal joint? If you look at the MCP joint of the human finger, it has a rolling contact joint, and it has ligaments. And collateral ligaments is basically at the extended position, it is at a loose position. But then as soon as it flexions, what happens is the collateral ligament actually tightens. And because at the extended state, it has a gap, and at the flexion state, there's no gap. So inspired by this kind of a principle, we designed a bioinspired rolling contact joint, where after printing, we have a gap. And we print the ligaments and the rolling contact joints, and because there is a gap, we can actually 3D print it. But as soon as it starts moving and flexioning, we can actually remove the gap using the cam effect. So by using this kind of very simple mechanical design, now what we can do is we can print the whole design, whole hand with multiple joints. And because this is a rolling contact joint, compared to other, of course you can print compliant joints and print the whole hand, but compliant joints are not that robust. But because this is a rolling contact joint, it's quite robust, and no structural assembly is needed. You just have to attach motors onto the hand. And what we found out was while testing this what we call step hand, we found we also had a testing of this hand on an actual patient that uses prosthetic hands. What we found out was that he said, we just wanted a hand that is comparable to what he was using, any kind of 3D printed hand, but what he told us was, oh, this is good because this is very lightweight. It's lightweight because we don't have any metal pins. Even just the metal pins, if you collect all the metal pins, that's around 20 grams. So that was another additional benefit that we were able to get. So we are at this stage right now. We are also trying to improve this design. But hopefully, if we always talk about, what if we can 3D print the whole robot, right? Probably you've seen Westworld. It's the intro of the Westworld shows a 3D printing of the whole human body. Maybe in the future, if we want to do this, we will have to 3D print a joint. And I think with our approach, maybe it might be possible to do something like this. And lastly, last example that I want to show is about multi-object grasping. We saw this video about 5 years ago. We were trying to just build a gripper, but as soon as we saw this video, I was like, what? Look at that, he's grasping like 5 objects at once, at all the fingers. And wow, okay, yeah, that's very obvious, right? Humans actually do this all the time. But robots, of course they do multi-object grasping, but at this kind of structured environment, right? You gotta have this kind of everything lined up, and you can actually move many things at a time. So if you observe human strategy in a structured environment, humans actually do this. So we started looking into, what is this? What does human do? And what we discovered was that according to this grasping development, finger to palm translation is the first thing that a child learns. And simple rotation, complex rotation is the last thing that humans learn. But we have many robots that do simple rotation and complex rotation. Many people are trying that, but we couldn't see any robot that's trying to do finger to palm translation and palm to finger translation. So we did that. So we looked into the principle. The principle that we need to use was finger to palm translation. It's one of the in-hand manipulations. It's called in-hand translation. It starts by segmenting your hand into a grasping section and a storing section. And then you can do this kind of finger to palm or palm to finger movement by using the thumbs. So we wanted to create of course, you can do this kind of hand segmentation without translation as well. But if you do this, you will not be able to do this kind of one-by-one picking. So there is 3 different types of in-hand translation. There's a pinch translation, sliding translation, and falling translation. We tried all different types, but we're going to do the pinch translation. And this is a design. As you can see, it doesn't look like a human hand, but we are using the same principle, finger to palm translation, and we are using the best engineering possible to build a finger design for stable pinch translation. We have decoupled the pinching with the translation, so it actually simplifies actuation. Storing section, we made it so that you can store many objects. So we were able to, so imagine if you had a robotic gripper moving this one by one, it's gonna take a long time, but by doing this, you can reduce the time. Sorry about the time. So we were able to do that. So my takeaway is, not everything needs to be learned. Nature has already learned through evolution. We should tap into evolution's design archive. And we should try generality through simplicity, not through complexity. And if you embed principle in the mechanism, that would be right. So let's keep learning from nature, keep designing robots that already have intelligence. Thank you very much.
Thank you very much. Very interesting presentation.